Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to learn how to balance redox reactions in acidic and basic solutions. We're also going to begin transitioning into electrochemistry by understanding how these balanced reactions become the foundation for electrochemical cells. With that introduction, let's go ahead and get started. When we balance redox reactions in acid, the overall strategy is similar to what we learned for neutral solutions, but there's one key difference. In acid, we're allowed to use water and hydrogen ions to finish the balancing process. That means we balance atoms other than oxygen or hydrogen if we need to. Then we match the electron flow using the least common multiple. After, if oxygen is deficient on one side, we can add water molecules to that side to supply the missing oxygen. But when we do that, we have to add hydrogen ions to the opposite side to balance the hydrogen that we introduced with the water. And this step is unique to acidic solutions, and it reflects the fact that hydrogen ions are available in solution. Now, we still follow the same few steps as before. So first, we're going to assign oxidation numbers to identify which element is being oxidized and which element is being reduced. Second, we place brackets around those specific atoms or ions so we can isolate the electron transfer. Alternatively, you can write them as two separate half reactions. Third, we're going to balance the electron flow by finding the least common multiple so that the total electrons lost and the total electrons gained are equal. Once that is done, the fourth step is what makes the acidic environment special. We look to see whether oxygen or hydrogen are unbalanced. And if oxygen is missing on one side, we add the correct number of water molecules to that side. Then, for every water molecule we add, we place two hydrogen ions on the opposite side to account for the hydrogen. Okay, keeping that in mind, let's apply it to our first example, which asks us to use the smallest whole number coefficients to balance the reaction between permanganate ion and nitrite ion in acidic solution. The unbalanced reaction is permanganate ion plus nitrite ion yields manganese dioxide plus nitrate ion. Let's start by assigning oxidation numbers. In permanganate, manganese is +7 and each oxygen is -2. In manganese dioxide, the manganese is now +4. Each oxygen is still -2. That means manganese has gone from +7 to +4. Since the oxidation number is decreasing, manganese is gaining electrons, 3 specifically, and that is a reduction. Now in nitrite, nitrogen is +3. And in nitrate, nitrogen becomes +5. That means nitrogen has gone from +3 to +5. This is an increase in the oxidation number, which means nitrogen is losing electrons, 2 specifically, and that is oxidation. As for oxygen, each oxygen that is present in these species has an oxidation number of -2. So nothing changes about oxygen's oxidation number. Now that we know which species are changing oxidation numbers, we can balance the electron flow first before we worry about oxygen or hydrogen balancing. To make the number of electrons equal, we use the least common multiple of 3 and 2, which is 6. That means we multiply the reduction step by 2, and we multiply the oxidation step by 3. Translating that back into the molecular equation gives us 2 permanganate ions and 3 nitrite ions, forming 2 manganese dioxide and 3 nitrate ions. At this point, the electron flow is balanced, and both manganese and nitrogen are also balanced. Now we will check oxygen. The left-hand side has a total of 14 oxygen atoms, while the right-hand side only has 13. So the right side is missing one oxygen, so we will go ahead and add one water molecule to the products to fix that. So that fixes the oxygen count, but it also introduces two hydrogen atoms on the product side that we have to account for. So to balance those hydrogen atoms, we add two hydrogen ions to the reactant side. The final balanced equation in acidic solution is 2 permanganate plus 3 nitrite plus 2 hydrogen ions yields 2 manganese dioxide plus 3 nitrate plus 1 water molecule. Before moving on, we always verify two things just to make sure we didn't miscount anything. First, we'll worry about the atom count. For manganese, there's 2 on each side. For nitrogen, there is 3 on each side. For oxygen, there is 14 on each side. And for hydrogen, there is 2 on each side. Okay, so this is good. Our atom count is perfect. Now let's check total charge. On the left, we have 2 permanganate at -1 each. We have 3 nitrite at -1 each. And we have 2 hydrogen ions at +1 each. That sums up to -3 charge for the reactant side. Then on the product side, we have 2 manganese dioxide, which are neutral, 1 water molecule, which is neutral, and 3 nitrate at -1 each, and that gives us a total of -3. So both mass and charge are balanced. The reaction is perfect and correctly balanced in acidic solution. Next, we want to discuss how to balance redox reactions in basic solution. We follow the same protocol here, except that we do not use hydrogen ions and water to balance the oxygens and hydrogens. In basic solution, we instead use water and hydroxide ions to balance those atoms. Let's see what this looks like. Here we're balancing the same reaction, but in basic solution. So the unbalanced reaction is again, permanganate ion plus nitrite ion yields manganese dioxide plus nitrate ion. And we begin exactly as before. In permanganate, manganese is +7 and each oxygen is -2. In manganese dioxide, manganese is now +4. Each oxygen is still -2. So that means manganese has gone from +7 to +4, which is a gain of 3 electrons. That is a reduction. In nitrite, nitrogen is +3, and in nitrate, nitrogen becomes +5. So we're going from +3 to +5, which is the loss of 2 electrons, and that means that nitrogen is oxidized. As for oxygen, each oxygen that is present in these species has an oxidation number of -2, so nothing changes about oxygen's oxidation number. Now that we know which species is reduced, manganese, and which species is oxidized, nitrogen, we can now balance the electron flow before we ever worry about oxygen or hydrogen. To make the number of electrons equal, we use the least common multiple of 3 and 2, which is 6. That means we multiply the reduction step by 2, and we multiply the oxidation step by 3. And translating that back into the molecular equation gives us 2 permanganate ions and 3 nitrite ions, forming 2 manganese dioxide and 3 nitrate ions. So the electron flow and the atoms for manganese and nitrogen, those are all balanced. And you've noticed that up until this point, These steps are exactly similar to acidic solutions. Here is where things are different in comparison. Because we are in basic solution, we do not use hydrogen ions to balance. Instead, we balance any oxygen deficiency using water and hydroxide. So let's begin by comparing oxygen on both sides. The left side has 14 oxygens in total, while the right side has 13. So the right side is short by 1 oxygen. To balance this, we add 2 hydroxide ions to the right side, that is oxygen deficient, and we're going to add 1 water molecule to the other side. We added 2 hydroxide ions because we know we eventually have to balance the hydrogens on both sides as well. And in water, the ratio of hydrogen to oxygen is 2:1. That balances the oxygens and hydrogens appropriately, and it gives us the following. 2 permanganate plus 3 nitrite plus 1 water yields 2 manganese dioxide plus 3 nitrate plus 2 hydroxide. Now we triple check and verify everything. We're going to count atoms first. For manganese, there's 2 on each side. For nitrogen, there is 3 on each side. For oxygen, there's 15 on each side, and for hydrogen, there is 2 on each side. Next, we check the charge. On the left, we have 2 permanganates at -1 each, and 3 nitrites at -1 each, for a total of -5. Water is neutral. Okay, that's the reactant side. What about the product side? On the product side, we have 3 nitrate at -1 each and 2 hydroxides at -1 each. Again, there's a total of -5 on the product side. So both mass and charge are balanced. So this is our final balanced equation in basic solution. With that, let's take a moment to compare this with the acidic result on the previous page. In acid, we ended with 2 hydrogen ions on the left and 1 water molecule on the right. In base, we instead have 1 water on the left and 2 hydroxides on the right. Both versions conserve atoms and charge, and they both exchange 6 electrons overall. But the side-by-side view is helpful to allow us to see the slight differences between the two. And it's also helpful when we transition to electrochemical cells, because these coefficients become the stoichiometric basis for current and for the movement of charge through the circuit. Okay, in fact, now that we've learned how to balance redox reactions in neutral water, in acidic solution, and in basic solution, we're ready to finally begin discussing electrochemical cells. Electrochemical cells are contained systems in which oxidation and reduction reactions occur. But instead of mixing all of the reactants together in a single beaker, the redox process is spatially separated into 2 compartments. And this separation creates a path for electrons to move through an external circuit, which is how we convert chemical energy into electrical energy. Now, at the top of this page, you see a summary table that compares 2 major types of electrochemical cells: galvanic cells, which are sometimes called voltaic cells, and electrolytic cells. For right now, we're just using this table as a preview. We're going to return to it once we've studied each cell type independently, and then the contrast between them is going to become a lot more clear. For the moment, the main idea is that galvanic cells operate spontaneously and release energy, while electrolytic cells require an input of energy to force a non-spontaneous reaction to occur. Let's begin with galvanic cells because these are the ones that directly generate electrical energy from spontaneous redox reactions. A galvanic cell works by separating the oxidation and reduction half reactions into different physical locations called half cells. And then they're connected through an external wire. When this separation is established, electrons can flow from the site of oxidation to the site of reduction. And that flow of electrons is what we recognize as electrical current. Every galvanic cell has two electrodes. The first electrode is the anode. The anode is always the site of oxidation, which means it is where electrons are released. Because the anode donates electrons to the circuit, it carries a negative sign in a galvanic cell. The second electrode is the cathode. The cathode is always the site of reduction, which means it is where electrons are gained. Because the cathode accepts electrons, it is the positive electrode in a galvanic cell. This terminology is universal. No matter what the cell is made of, oxidation always occurs at the anode and reduction always occurs at the cathode. And electrons are always going to flow from anode to cathode through the external wire. Now, each half cell typically consists of a metal electrode immersed in a solution containing the corresponding metal ions. If we look at a zinc copper cell, which is what's shown in this diagram, the zinc electrode is placed into a solution that contains zinc 2 plus ions. And the copper electrode is placed into a solution containing copper 2 plus ions. At the zinc electrode, solid zinc atoms are oxidized to zinc 2 plus ions, and these ions enter the solution. Because oxidation removes metal atoms from the solid surface, the zinc electrode gradually loses mass. On the copper side, copper 2 plus ions in solution gain electrons and they're reduced to solid copper, which deposits onto the electrode and increases its mass over time. A salt bridge is going to be required to maintain electrical neutrality in both compartments. So without it, charge would rapidly accumulate in each half cell and the electron flow would stop. So the salt bridge contains a non-reactive electrolyte, something like sodium nitrate. Negative ions from the salt bridge are going to migrate towards the zinc half cell to replace the electrons that were lost to the circuit. And positive ions are going to migrate towards the copper half cell to balance the gain of electrons there. And this ion migration is what keeps the solution electrically neutral, and it's what allows the cell to continue operating. Because the overall reaction in a galvanic cell is spontaneous, the Gibbs free energy change is going to be negative. Then, to describe a galvanic cell in a compact way, we often use a shorthand notation, which is going to list the anode to the left and the cathode to the right. So for this zinc copper cell, the notation is written as zinc solid, vertical bar, zinc 2 plus in 1 molar solution, double vertical bar, copper 2 plus in 1 molar solution, vertical bar, copper solid. Each part of this notation has a specific meaning. So the single vertical bar represents a phase boundary. So for example, between a solid metal and an aqueous solution, which we see here and here. And then the double vertical bar represents the salt bridge or porous barrier, which separates the two half cells while still allowing ions to move to maintain that charge balance. The species on the left side are going to be the anode, where oxidation occurs, the zinc solid is being oxidized to zinc 2 plus ions. Then the species on the right side of this are the cathode, where reduction occurs. So the copper 2 plus ions are gaining electrons, becoming solid copper. So when you read this notation, you are really reading the chemistry of the cell in a very compressed form. Solid zinc is losing electrons to become zinc ions. On the left, those electrons travel through the external circuit, and the copper ions, they gain those electrons and they become solid copper on the right. Now that we have the shorthand notation written, we can translate it back into the two half reactions. On the anode side, zinc metal is converted into zinc 2 plus ions. That process requires the loss of 2 electrons. So this is the oxidation half reaction. On the cathode side, copper 2 plus ions in solution gain those 2 electrons to form solid copper that plates onto the electrode. This is the reduction half reaction. When we combine these half reactions, the electrons cancel exactly, and that gives us this overall net reaction. Zinc solid reacts with copper 2 plus in solution to produce zinc 2 plus in solution and copper solid. Because this is a galvanic cell, the process is spontaneous, which means the Gibbs free energy change is negative. When the Gibbs free energy change is negative, the standard cell potential is positive. Then the next natural question is, where do we get the numerical values that describe each half reaction, and how do we use them to calculate the overall cell potential? We do this using the relationship E naught cell equals E naught cathode minus E naught anode. This subtraction, it's not arbitrary. It encodes the fact that the cathode reaction is happening in the reduction direction exactly as it's listed in this table, while the anode reaction is occurring in the opposite direction as an oxidation. Now, please note, we do not flip this sign manually. So we don't take the reduction half reaction for a process we know undergoes oxidation and flip the sign ourselves. No, the subtraction automatically accounts for that reversal, which is why we always keep the listed values in their reduction form. To understand what these values actually mean, we look to the standard reduction potential table. Every entry in the table is written as a reduction, so each line shows how strongly that species wants to gain electrons. A more positive value corresponds to a stronger pull for electrons and a stronger tendency to be reduced. That also means that species that are high in the table, they act as strong oxidizing agents because they are very good at taking electrons from something else. Fluorine gas is the strongest oxidizing agent in this list. At the opposite end of the table are very negative values. These species do not want to gain electrons. They actually prefer to lose them. They are therefore strong reducing agents. And lithium metal is a classic example. It has a very negative reduction potential. And that tells us that lithium doesn't want to be reduced at all. It wants to give up its electrons, which is why it behaves as a powerful reducing agent. There's also a natural complementary idea here. If we conceptually flip a reduction half reaction to write it as an oxidation, the sign flips as well. The resulting quantity is called an oxidation potential. So a species that has a very negative reduction potential will have a very positive oxidation potential, which means it is very easy to oxidize. So in general, remember these two ideas. A large positive reduction potential corresponds to a strong oxidizing agent and an easy reduction. A large positive oxidation potential corresponds to a strong reducing agent and an easy oxidation. In addition, the entries on this table, they're called standard reduction potentials because they're measured under a specific reference set of conditions. 1 molar concentration for aqueous ions, 1 atmosphere of pressure for gases, and a temperature of 298 Kelvin. Under these standard conditions, the values can be used directly without any adjustment. If the system is not at standard conditions, though, we eventually need to use the Nernst equation to convert the voltage, but that is a topic for another lecture. Now, if we go back to our example galvanic cell with zinc and copper, we can go ahead and obtain the standard reduction potentials for each half reaction from the table. The reduction potential for copper 2 plus going to copper solid is plus 0.340 volts. This belongs to the cathode because copper is being reduced. In fact, when you are looking at the 2 half reactions that make up your galvanic cell, the reduction potential that is most positive, that's going to be assigned your cathode. The other is going to be your anode. The reduction potential for zinc 2 plus going to zinc solid, it's negative 0.762 volts. Now, our zinc cell is the anode, and it's actually being oxidized. Since the table always lists values in the reduction direction, we ourselves are not going to flip this sign. Instead, we're going to confidently assign the cathode and the anode. In this case, it's the copper half reaction, that is our cathode. Our zinc is our anode. We confidently assign them, and then we take their values and directly plug them into our equation as written. To compute the standard cell potential, we take E naught cathode minus E naught anode. So here we have 0.340 volts minus negative 0.762 volts. Calculating this gives us 1.102 volts. This positive value confirms that the overall reaction is spontaneous under standard conditions, which is exactly what we expect for a working galvanic cell. This calculation also demonstrates the physical meaning of the standard reduction potential table. The more positive cathode value is telling us, again, that copper 2 plus has a strong tendency to pull electrons towards itself, while the very negative value for zinc 2 plus tells us that zinc metal easily lets go of its electrons. And when these 2 half cells are connected, the electron flow naturally proceeds from zinc metal to the copper 2 plus solution, and the result is a voltage of 1.102 volts. That voltage, it represents the maximum possible work per unit charge the cell can deliver under standard conditions. Before we move on to our next topic, let's tackle a couple of practice problems. The first question asks, as written, which of the following statements about the table of reduction potentials is not true? Let's go through each option carefully. A says, the potentials for ionic species are measured at 1 molar concentration. That is correct because all standard reduction potentials assume standard state conditions, and that means 1 molar for aqueous ions. B says, the reactions are presented or as presented constitute only half of an electrochemical cell. That is also correct. Every line in the reduction table is just a half reaction. It either becomes the anode or the cathode, depending on how well we construct the full cell. C states that the reactions as written are all spontaneous. This is not true. Some reduction potentials are positive, but many are negative, and a negative value means the species does not want to be reduced under standard conditions, so the reduction would be non-spontaneous. Therefore, C is the correct answer because it is the statement that is not true. Let's still work through D though. D says the reactions are all written as reductions. That is correct. The reduction table always lists the electron gain direction for every entry. Again, the only false statement is C. Now let's look at the second problem. We are given a galvanic cell written in shorthand notation. Lead solid is on the left in contact with lead 2 plus ions, and copper 2 plus ions are on the right in contact with copper metal. We're also given the reduction potentials. The reduction potential for the copper 2 plus to copper half reaction is positive 0.34 volts. The reduction potential for the lead 2 plus to lead half reaction, that is negative 0.13 volts. We're asked, what is the standard potential of the cell? To calculate the standard cell potential, we need to identify the cathode and the anode. In a galvanic cell, the more positive reduction potential corresponds to the cathode, so copper is reduced. Lead here is the anode where oxidation occurs. Now, we apply the equation E naught cell equals E naught cathode minus E naught anode. So we take positive 0.34 volts minus negative 0.13 volts. Subtracting a negative is equivalent to adding. So our result is 0.47 volts. Because this value is positive, the redox process is spontaneous, which is exactly what we expect for a galvanic cell. Now that we understand how galvanic cells operate, they operate spontaneously and they generate electrical energy, we can contrast them with the second major class of electrochemical cells, which is electrolytic cells. In an electrolytic cell, the situation is reversed. Instead of a spontaneous redox process driving electron flow, we instead apply electrical energy from an external power source in order to force a non-spontaneous reaction to occur. The chemistry is thermodynamically uphill, so without that external voltage, nothing would happen. The power supply must push electrons in the direction opposite to where they would naturally flow. So in the diagram here, you can see that the external power source is pulling electrons away from one electrode and pushing them towards the other. The electrode that loses electrons is still the anode, and the electrode that gains electrons is still the cathode. Those definitions never change. However, the polarity flips compared to a galvanic cell. Because electrons are being pulled away from the anode by the power supply, the anode becomes the positive terminal. And then the cathode becomes the negative terminal because electrons are being forced into it. The important takeaway is that in an electrolytic cell, the cell potential is negative under standard conditions. A negative E cell corresponds to a positive Gibbs free energy change, which means the reaction is non-spontaneous. The only reason it proceeds is because we are supplying an external voltage that's large enough to overcome that thermodynamic barrier. In problem types for this objective, make sure to be careful in your assignment of the anode and the cathode because that will play a huge role in how you calculate E cell. Here, you expect the half reaction with the more positive standard reduction potential to be the anode and the more negative standard reduction potential to be the cathode. You again expect to calculate and negative E cell for an electrolytic cell. With this foundation, we can now look at a very common application of electrolytic cells, the electrolysis of molten salts. A molten salt contains only two types of charged species, freely moving cations and anions, and nothing else that can compete for reduction or oxidation. There's no solvent such as water, so there are no water-based side reactions. This makes molten systems the cleanest way to illustrate the basic logic of electrode selection. In a molten salt, every ion that exists is already dissociated and mobile. The external power supply then drives the ions according to their charges. So cations migrate towards the cathode and anions migrate towards the anode. Once they arrive, the only question is which ion is thermodynamically easiest to reduce or oxidize. This is where standard reduction potentials enter the picture. At the cathode, the ion with the more positive or less negative reduction potential is reduced first. At the anode, the ion with the more positive oxidation potential, all right, this is going to be the one that's oxidized first. So molten salts serve as the simplest controlled environment to learn the selection rules because the products follow directly from comparing electrode potentials without any interference from water. Let's work through a couple of examples. This first one we have sodium fluoride and lithium chloride. If we melt sodium fluoride and lithium chloride, the ions present are going to be sodium plus, lithium plus, fluoride minus, and chloride minus. At the cathode, the question is which cation is easier to reduce, and at the anode, the question is which anion is easier to oxidize. We answer this by looking at the reduction potentials. Sodium ion has a reduction potential of negative 2.71 volts, while lithium ion has a reduction potential of negative 3.05 volts. The cation with the more positive values, easier to reduce, so sodium ion is reduced. Sodium metal will form at the cathode. At the anode, the two candidates for oxidation are fluoride and chloride. To compare them fairly, we look at the oxidation potentials, which means we flip the sign of their reduction potentials. Fluoride has an oxidation potential of negative 2.87 volts, while chloride has an oxidation potential of negative 1.36 volts. The more positive oxidation potential, or the less negative oxidation potential, means the species is easier to oxidize. So chloride is oxidized first, and it produces chlorine gas at the anode. Therefore, molten sodium fluoride and lithium chloride produce sodium metal at the cathode and chlorine gas at the anode. In the second example, we take a mixture of three molten salts together: sodium chloride, magnesium bromide, and lithium iodide. Again, we list all of the ions that are present. The cations are sodium plus, magnesium 2 plus, and lithium plus. The anions are chloride minus, bromide minus, and iodide minus. At the cathode, we compare which cation has the most positive reduction potential and is therefore most easily reduced. Magnesium 2 plus has a reduction potential of negative 2.36 volts, which is more positive than sodium and lithium. So that means magnesium 2 plus will be reduced and it forms magnesium metal at the cathode. At the anode, we compare the oxidation potentials of the halides. Iodide has the most positive oxidation potential when the sign is flipped from its reduction potential, making it the easiest to oxidize. Therefore, iodide will be oxidized and it forms iodine at the anode. So, for our mixture of molten sodium chloride, magnesium bromide, and lithium iodide, magnesium metal is produced at the cathode and iodine is produced at the anode. And with that, we've completed this lecture. I hope it helps. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.